So we've got a nice grid, day 10. And we have, well, something that looks a bit like this, which is a bit intimidating. And then we've got really a grid that has a loop in it, and the loop is represented by these characters. They represent pipes, so you know you can't go anywhere. You can just go exactly where you're specifically able to go. Um, the the pipes are also this loop is also surrounded by many other pipes, and it's worth noting that um, while in this input we've got a we've got it's sort of fairly clear where the pipe is going to go, in that it can't go left, it can't go up, because these are bends that don't align with it. It can go right and down, so the loop goes this way. The input may not be so friendly. As it happens, now I think of it, I think it may actually be that friendly. So if we can see the S here, let me highlight that. The F goes up and right, so that's 1, and the L goes left and up. So, and the 7 we don't match to, the F we don't match to going down, the J we don't match to going, because we can't go that way. This horizontal pipe we don't match to, and the others, yeah. So we've only got an in and an out. So that's quite handy, actually. In any case, it probably doesn't make that much difference to our solution. Yeah, so our job, by the way, is to find the loop, or rather to work out how many steps along the loop does it take to get to from the starting position to the point farthest from the starting position, going by the distance along the loop. So obviously you can go one way or the other way, and the farthest point is the one where the distance is equal, which is probably half the way of the length of the loop, right? Yeah, so ooh, okay, let's try that. So I've had a bit of time to think this morning. I think I've got a reasonably good idea as to what we need to do, which is we're starting at this S point. It's good. Good to do this? No, it's not. We're starting at this S point, and we need to work out which cells can we go to from here. And we have two things to consider. The first is the restrictions on our current cell. So the S, as it happens, can go anywhere. Well, it can go left, right, down, and up. I don't know why I'm pointing to them wrong. It can go any of those four ordinary directions, because we don't know which it is. Or can it? No, I'm pretty sure it can. The specification of the problem is really that we don't know what pipe it is, but we do know that it is a pipe. So we couldn't, for example, assume that we can go any direction from it. We can go at most 2 directions from it. Doesn't seem to come up in the input, but it's just worth assuming that. let's make an assumption to make things simple for ourselves. It doesn't matter um, if we go more than two directions from S type. It probably won't come up, but in principle, I suppose we might want to be aware of it. So there's the restrictions there. If we're on this cell here, let's say we're on that cell right now, we can't go right, we can't go up. Even if the F would allow it, we can't go up because the 7 is it's a sort of right, it takes things in from the left and puts things out going down. Just give me a thought there. Um, so the restrictions on our current cell and the restrictions on the cell we're going to. So what I'm curious about now is, does this one even matter? With all of these pipes, they have one input and one output. So the output is totally deterministic of the input. This one takes in from the top and goes down. This one will go or up and down. Yeah. So if we enter a pipe from the top, we're always going to come out the bottom. Now, if we enter from the air, if we enter the S, we are, well, it doesn't really matter if we enter the S because we're going to have reached the end then anyway. But we can exit the S from any cell to any cell. Okay. So what I'm wondering is there a way of only having to deal with one of the cells? The cell that we're on or the cell we're going to? So the S one is special. The S one does require that you look at the cells around you. We're going to decide to go on this one. We could do both, of course. Then we would only have to do one iteration, which would be neat. But possibly two cover. Okay, so we're going to go on this one. Now, we've come in from the right, from the left, which means we are going to exit from the right. So by the point that we know we're going right, and this cell, we already know that we're going to end up on this cell. And because we're entering this from the left, we're definitely going to go down. Because we're entering this from the top, we're definitely going to go down. Because although if this was a different cell, we go somewhere else. So the function of so to get the next cell, is the movement That's the function, right? And it's a pretty straightforward lookup, right? You could do that as a lookup. So you could say, okay, so if we were to calculate this out, we're looking at going right with this. The next movement's going to be right again. Going left with this, the next one's going to be left again. Now let's do the ups and downs. Sorry, that's wrong. Now, if this is 0 and this is +1, and we're going entering a pipe, then this one's going to be 0 and this one's going to be +1. Likewise with this, it's going to be -1. And now we've got these. Let me copy these in. So if we're going down into an L, okay, before I go any further with this, what we're assuming here is that there are no dead ends. Can there be any branches? I don't think there can be any branches. Each of them has an entrance and an exit, and there's no branching at all, apart from the S, which could in theory branch, but I'm certain it doesn't. Part 2 may cause us some issues, but yeah, so there's no branching. It's got to be going, yeah. So if we look at this, F cross down J F L. So you can actually just follow it, right? I don't even see the numbers anymore. I could just do this, no problem. Wait. Oh yeah. Easy. Okay, so before I type these out anymore, um, yeah, so I mean this approach will work, right? So actually this doesn't matter. What we care about is the movement we've just done and the cell type, except for the first one. The first cell is special. And then we can move along two at once, going either direction, and we'll be able to we'll come back when they're at the same point, we'll have solved the problem. We'll know how many steps there are. Okay, so the algorithm is, this is definitely not going to work for part two, but I'm pleased by it. So let's give it a go. Okay. After parsing and such, wait, we need to work out how we're going to structure this. Um, hmm. Yeah, okay, that's fine. Hey, so for the S, we want to have like a we'll have some special logic around that. So let's say we found the directions and then we're going to uh, until searches have the same. Wait, could they flip over? Let's find out. Okay, so they're going to start off here, here. Oh gosh. Here, here, and here. I mean, if there is an equidistant point, which there should be, according to the problem, then then they're going to end up on the same point, right? Until searches are the same coordinate, um, look up next movement in pict. Yeah, well, yeah, that's that really. Okay, so there's a bit of like puzzling through the data structure to do, but it should be okay. All right, I'm just going to take a short break. All right, we're back. Okay, so let's move towards starting some coding here. Right, so let's think about state. So we've got this grid. I don't think we need a list of cells. Okay, so the search has got some state in it, which is its last movement. It's got its position, line chord as well. Okay, its last movement. It's really a vec, isn't it? It's probably a built-in vector type, but I'm going to use it. Okay, last movement. Mm, where am I going to put lookup table? remember how I did this before. Anyway, I think the lookup will go here, and that's going to be a dict of vec string to vec. And for that, we're going to get the searcher's last movement, the cell that it's currently on. Cell that it's currently on. And then look it up, and then we can move it by that. We can find the movement, and then yeah. Okay, so let's go just tick. Great. Okay. A little bit in my head, but I think we're good to go. I think we could get a gold run today if we pay attention. Okay. Switching to the code. Set the time. Oh wait, I've not done my plan of action. I need to do that. That's going to be yeah, let's go with that. Okay, reset the timer and then let's get started. This is really a coord, isn't it? Anyway, doesn't really matter. I'm very quiet today. Probably talk more. Wouldn't do well if this is an interview. No, that would be annoying. I swear I had some utilities in here for this. Oh well. How do you do that again? And this one, here's where I make my mistakes, right? This one, I'm going to go in from the top going down. That's the same. And this is also the same. So these should be the same. This should be the same. This should be the same. This should be the same. Okay. Now I've got the L shape, which you can go down into, which is 0, 1, or can't use my keyboard, or you can go left into just -1. If you go down into it, you're going to come out right, going right. If you go left into it, you're going to come up going up. And then we've got J. We've got 7. We've got F. S we're not going to worry about for now. Actually, I forgot to put in S. Or let's find out S. Yeah, S and ground we don't need to worry about, I hope. Okay, so J, we can go in going down, at which point we're going to go left. We can go in going right, at which point we're going to go up. With 7, you can go in from the bottom upwards, and in which case you come out going left. If you go in going right, and you come out going down, which is +1. With the F, you can go in from the bottom again, and you come out going right. It's that way. Or you can go in going left, and you come out going down. Okay. That's good. Now, we're also going to need we're going to need to we're going to need to fill these out. I'm going to just do a bit of parsing. Okay. Is that roughly right? Okay, 7. Yeah, good. Okay, that appears to be working correctly. Back to the plan. So we're going, let's go up first. So if we go up and we find a pipe or an F or a J, no, wait, not a J. What can we go up into? Or a 7, L, no, wait, F. We can go up into 7, we can go up into, that's it. And with this, we go down and we get a J or an L. We're going to append going down. We go right and we find a hyphen, a 7, or a J. Yeah, just a weird font J. Then we add go right. And then if we go left, we find an F, L, we're going left. We want to check. So we then want to have searcher A move by directions 0 and searcher B move by directions 1. Then we're good to go. While self-searcher A is not the same as self-searcher B was, we want to tick them. These should be the same. We can look into that. Okay. And then we've got this tick thing, which involves us taking the searcher and moving it by lookup given movement last movement and the grid where we're at the searcher's current position. Oh, long line. I'm not this later, there's only bugs. All right. I'm sure that works. All right. And we want to return .23. Oh, the initial position. I've not set the initial position of the searcher. Running out of time. Oh, we can't go that far left. Okay, fine. Uh, 8. Is that right? Yes, I think so. Yes. All right, let's try the input. All right, let's see. Okay, 2544. Gold. I'm amazed that worked as well as it did. All right, let's take a look at part two. Okay, maybe its nest is within the area enclosed by the loop. To determine whether it's even worth taking the time to search for such a nest, you should calculate how many tiles are contained within the loop. For example, okay. So we need to find out which tiles are inside the loop. What I'm curious about is any tile that isn't part of the main loop can count as being enclosed by the loop. Okay, I think that means what I think it means. Okay, so I think I know the right algorithm for this. You can go, let me actually diagram this out with something like this. So I think they do this. Yeah, so the basic idea is you fire a ray along from left to right or up top to bottom. And if you hit a an edge, you flip the state to start saying, okay, now we're inside. So now this is easier in this case. I think this is easier in this case. So you zoom in on this. Okay, so you hit it here. Here's a wall. In fact, yeah, let's have this be black here to mean outside. You hit a wall, you flip the state to red for the next cell, I guess. Inside, inside. Okay, we flip again. Outside, we flip again. Inside. So yeah, inside, inside, flip again, outside. And then you can capture yourselves like that. Um, now, Presume we know which is the loop and which isn't, of course. What I'm curious about is does it I think you only need to go like one way across. But let's try it out. Let's try and look for some weird examples. So let's say we've got something like this. L J. Now, if this could be an open loop, we would never know. But since it must be a closed loop, then this has to be enclosed, right? So there's no other weird cases where we could like this rule wouldn't hold. This one you'd flip twice, so that would work fine. Yeah. Okay. So what is that? What is that called? I don't remember what it's called, but it's called something. Ray. Yeah, I think I had to do it last year or something. Anyway, so okay, so for each row, for each cell. So we need to know what's in the loop first. So we need to like, hmm, I'm just wondering whether, yeah, anyway, let's keep sketching it out. Okay, for each cell, if so, okay. Probably we don't need to worry about like the outside being a, so we're always going to reset the state. Let the let ray state be outside. For each cell, if well, let's go with if ray state is outside. If we're on a wall, set state to uh, inside, or let's actually flip ray state because it can only be inside or outside, I think. If we're on a wall, flip ray state. No, wait. This is the case one, no matter what we're in. If ray state is inside, mark cell as inside. So this works in this case. So we're on this cell. It doesn't work in this case. We're on this cell. We're not on a wall. We're not on a wall. Ray state is outside. So therefore we do nothing. We move along. We are on a wall. So we flip the ray state. We move on to this cell. We're not on a wall. If the state is inside, we mark the cell as inside. So that counts. This counts again. We're on a wall. So we flip the ray state. Move on. Don't count. Move on. Flip state. Do count. Do count. Flip state. Don't count. So this is fine here. Where it gets tricky is if we end up on a row like this. Or even a row like this is probably a good case. Okay, so here we skip the first, we flip to red, we flip to, okay, we're on a wall, so we flip it again. We're on a wall, we flip it again. We're on a wall, we flip it again. We don't count this. Flip it here, flip again, flip again, flip again. And this doesn't count. But if we had a different case, like let's say we had this case. And let's imagine that we kind of took all this down as well. In this case, flip red, black, red. We count this, which we definitely shouldn't. And then, yeah, so that's not good. We do care about situations where we're on vertical walls, horizontal walls, I should say. Those have to be handled specially. Now, let's look at a derived example. Let's look at an example like this. What is that? 7. What about to be a 7 there? Yeah, let's look at an example like this. In an example like this, we don't count this. We don't really want to start counting here, but we don't know what's next yet. So there's nothing currently in our logic to say that we should, other than I guess L's don't count. So it's to do with the kind of wall we're on potentially. So what counts going across? This definitely counts. Seven potentially counts. L doesn't count. Dash doesn't count. What we really care about is when we're exiting a wall. That's when we want to shift the state, right? When we're exiting a wall. Yeah. So we've got our characters. Yeah, make a note of them here. Oh, and the S as well. The S is going to be there. Gosh. Hmm. And we're going to need to know which way the S is going. Okay. Let me make a note of that. And by the way, what matters is, are we on a wall that is within that outline? Because it doesn't matter if this is like a, that should still count. So let's put a J here just to make that explicit. No, that'll be horrible. Let's just remember that. Okay. So L doesn't count. F doesn't count. J does count. Yeah. Okay. And then S is special. Now for us, S is the same, essentially the same as a bar. So we can probably do some logic to just change what S is. Or we could just, just say it's a bar. It is a bar, right? No, it's a J actually. S is a J for us. S is a J. But it won't be there in all of them. So we'll need to have some special logic there. Okay. So if we only count these, what do we get? Okay, L doesn't count, 7 does. So we flip the state, dot counts. Nothing. So we get one cell there. Now, if we apply the same logic to here, S here is a F. F doesn't count. These don't count. 7 does. So we flip. Oh, that doesn't work. Yeah, this additional logic needs to be applied here. So here it counts because we went through an L first. Here it doesn't because we went through an F first. There's some subtle logic that I'm missing. Actually, what if it's the L that counts? Then it's the J that counts here. So L and J counts. But they don't get, of course, they don't get counted. Here, let's say we had a version of this where there was a dot in the middle of here. We go through here, that switches us on. None of these get counted, but then this one does. And then this one flips it off again. Where's my other example? Oh, sorry. Here, the L counts, 7 ignored, dot. Yeah, okay. Now, can we construct an example where the all right, so let me just do this properly again. What counts L and J? Those don't count. what if we had that wouldn't work because we would need to. No, that's on the outside still. Yeah, okay. I'm kind of convinced. So these count, these don't. S is special. We need to know work out what S really is. So the right algorithm is yeah, okay. I think I'm convinced. Yeah, okay. So the plan is we have to write that, and that's going to be based on really on the cells that are around it. So if the directions are like this, it'll be a certain thing. If they're like this, how many directions have we got to go? We've got an up. Yeah, well, we got 6, right? We've got the same number as here. So we're going to need to write that. That will just be a kind of horrible lookup to write. I can probably repurpose my lookup. If you go down, right, yeah, okay. Yeah, I can do that and write that lookup. Okay, then I need to I need to make it so that I'm capturing the outline cells. Do that, and then I want to have add a do I need to write anything more here? No, I don't think so. I can just iterate through. Well, I think I'm good. I'll be amazed again if this works. I'm going to take a short break and then be back. Yeah, I've had my cake and it's now time to work. Let's reset. Okay. Hmm. I'll probably do this. Nope. uh, set vec is surely hashable. Sets aren't hashable because they're yeah, because they can be changed, right? Can they be frozen? Let's go for it. A frozen set. Always good to meet a new friend. Awful. Will that actually work? Oh dear, what a mess. what do I keep doing wrong here? Ugh, let's do it manually. Why have I made this so complicated? I remember doing nonsense like this last year as well. Just no need for it. 5 minutes this has taken me. Absurd. Okay, this is still part one. Oh well, I guess I'm doing it in part one. I'll unmess up that later. Zero, 1, 1, 0. Yeah, should be this, right? Oh, it's empty. Why is it empty? Present there. Yeah, no need for that. Is the dancer different there? No, it's the same. Okay, fine. All right. That was a bunch of time wasted. All right. Uh, hmm. This is going to be a vec then, isn't it? Kind of irritating. Oh well, that will be fine. And we combine sets. Yeah, okay. Okay, that's that set. Put this to the calculate. Looks about right. What are we actually supposed to get? The number of cells that are fine. Hmm. Don't know the width. Is that going to be right? Let's go with that. It doesn't really matter if we're over, just as long as we're not under. Okay. Hmm. Probably fine. We can't possibly be hard up against the edge. That wouldn't make sense. We're not going to count them, but we're not going to count the same cell twice, so it doesn't. We don't need to keep track of them. Do we have a ternary in Python? No, we don't think we do. Well, kind of. Inside if okay, that flips. And we need to be on the and we need to be on the specific wall. Hmm. Let's try it with the real one. Doesn't seem right to me. No, it doesn't seem right. Okay. Okay. Something wrong here. What's up with this one? Let's try this one. It's definitely not. It's definitely not what the start cell is. Oh, oh, it's the other way round. It's the opposite. Okay. Pretty sure this is true. Not certain though. Ah, this should also make its way into the outside, to the outline pauses. Why isn't the start cell making its way in there? It's so strange. Fine. It's just not useful. Okay. Now the inside spit is not working for some reason. We definitely get in here. Race state never becomes inside then. Is this logic the odd thing? Probably a typo or something, I guess. Ah, is this better? Okay, so we're flipping there. What are we doing here? What about on this row? So on X, on Y, 0, 1, 2, 3, 4, 5, 6, X, 2. Let's look for 6, 2. No, Y, 2, 6. Ah, no. All right, well, that's my gold run gone. Okay, 2, 2, 6. It's definitely running. We're inside. The type is I. What is I? Ah, you moron. No, very silly. Very silly. Okay. Oh no, it wasn't that all along, was it? That's outrageous. That's outrageous. Okay, well, at least there's other bugs. Okay, so on this one, we want to look at cell LJ. Oh no, it doesn't matter if this is. Ugh. Great. Now let's try with the input. This looks very suspicious. I'm pretty sure that's not right. I'm going to type it in and then we'll see. No, too high. Yeah. So there's something weird going on here, right? Let's try, just check if we can get the other examples to work. Eight here. What about this one? Four there. Okay. So we're definitely going to have a bit of fun. Brrr. Uh, okay. Will my utility library help me here a little bit? Yes, it will. I should just check whether my F, is it an F that I have? Start cell is definitely not F. It's actually J. What happens if I just force it to be J? I wonder. All right, let me try this. Let me just complete this bit. Not being very helpful. Got the thing wrong. Text 1, color 2. Okay, fine. Other way around. Why are you going to be so unhelpful? That's even less helpful. This is not useful. Okay, fine. We won't use this time. Figure out how to use this later. Okay. Right. So it's not actually F. It's definitely J. I know that for sure. Is this any better? 309? What did I have before? 309. Same deal. Well, we won't go back to our faulty logic, but it's worth knowing. So we do have a bunch of things going on here on this row. It's not that. Row 50, Y58. So in the input, that's 7. 59, rather. Okay, so this one is weird for some reason. Is it the one that S is on? Yes, it is. All right, that's pretty suspect, isn't it? So in this case, if we reach S, we should be treating it as a J, right? And a J does count. All right, well, my logic clearly went wrong there. 297. I'm pretty sure this is right. Hey, great. Now I am just going to spend a little bit of time figuring out what I got wrong here. So firstly, this should be marking this as J. So why is it not? Do we just have different cells? Definitely putting it as J. Doesn't seem to be turning up in the right place. I know it is. It's just haven't got that color. What's another color I can use? Let's go with this for the walls. That should make it more obvious. Yeah, okay. So it's still S. It somehow get duplicated. I guess it must do. Yeah. How weird. What's duplicating it? It goes in the dictionary. There's only one place that cells are created, and that's in here. Ah, that is an annoying bug. That is an annoying bug. The other bug, of course, is that this is wrong. It decides it's an F. when -1 and -1. So x -1, so y -1 and x -1. So 0 -1. So here it's going in from the bottom and yeah, so it actually can go out left and down. Probably best to redo these from scratch. So if it can go out from the left, yeah, in fact, these vectors are just totally wrong. If it can go out from the left and the right, it's going to be a bar. If it can go out from the top and the bottom, it's going to be a bar vertical. If it can go out from the top and the left, it's going to be a J. If it can go out from, see, this actually is a -1. Yeah, going upwards and leftwards is a J. If it's going upwards and rightwards, it's an L. If it's going downwards and rightwards, it's an F. And if it's going downwards and leftwards, it's a 7. Correct. I hope that was the right answer again. Okay, fine. Let's put this in part 2, which is where it should be. Come on. Start running that. Wind this back for a while. So how did this go? I think it went okay. Lots of fiddly stuff and a few mistakes. Um, probably a better visualization would have helped with that earlier on. So I probably should, with these problems, I should definitely bias towards getting the visualization up earlier. Not spotting a few of those errors really mess things up a bit. But otherwise, in general, okay. A gold and silver for day 10, I'll take that. Let's wind this back a bit more. Yeah, and then we can take this out and then we're done. Yeah, so having the visualization earlier would have helped me catch those bugs. It's still right for, yeah, that's right for part 1 and part 2. Yeah, great. Cool. See you tomorrow.